Can you see the screen, Zaina?
Yeah,
All right, fine. All right, this is the last class we had related to in the end, made a chart related to the functional groups and then the different classes of the organic compounds. And then if the homologous series formula exists and the ends in what, and then the example. I hope it's all clear.
yeah,
All right. And we also discussed the isomerism. So I hope that it's all clear. Right now, today we are going to start the topic that is Oh, primary, secondary. Oh, yeah, I wrote it just for the introduction of primary, secondary, and tertiary alcohols and halogenoalkane. I thought we didn't do that. That's why I wrote it so that next time when we will start our class, that would be the first thing to do. Yeah.
yeah,
So I'm going to do this, Beta, and after that, we will start the chapter number 12. That is actually the topic related to alkanes. Yeah, one thing, if I am not wrong, we have already done uh, about the just a minute. Yeah, carbocations. So we discussed about primary, secondary, and tertiary carbocation. So I think this is clear to you. I'm talking about this thing. Is it clear to you? So I can shift to the next one.
yeah, it's clear.
All right, fine. So coming back, sorry for this quick scrolling. All right, now we are going to discuss the primary, secondary, and tertiary alcohol. So, because on that day you told me that you don't have any idea about the primary, secondary, and tertiary alcohol. However, as far as the alcohol is concerned, I think you are clear about it that it the functional group is ROH. It ends in ol, and the homologous series formula is CnH2n plus 1 OH. And then the example could be propanol, butanol, pentanol, or anything like that. Yes? Is it clear? The
Yeah,
alcohol. All right. Now, so we'll discuss primary. Alcohol is better clear to you. Now we are going to discuss primary, secondary, and tertiary alcohol. Yeah. So let's start it off. Now, primary alcohol, secondary alcohol, and tertiary alcohol. So, um, mm, just wanted to check the colors because they are very close to each other. Brown, and that's about it. All right. So, primary alcohol. If we will talk about primary alcohol, so this is OH, and if the OH is linked to this carbon, and if this carbon is connected to 3H, or if this carbon, which is connected to OH group, is connected to an R group, this is called as primary alcohol. All three are eights, or two are H and one is R. So this is called as primary alcohol. Is it clear, Zina?
yeah,
All right. But as far as secondary alcohol is concerned, I'll write the same thing. But now the OH is linked to this carbon, which in turn is linked to um just a minute, Peter, let me. All right. Which is linked to two R groups, right? And the third one is H. These R groups could be the same, or they could be R or R dash. They could be different. This is called as secondary alcohol. And for example, I'll give you the example afterwards. And then OH is linked to the carbon, which in turn is linked to all three R groups. is called as tertiary alcohol. These are groups could be the same or they could be different. Now, giving the example, right? So the example of primary alcohol could be the simplest one, Betty. All three hydrogens are here. All three hydrogens or the OH is linked to the carbon atom, which in turn is linked to three hydrogens. So this is CH3OH, the same thing, and it is called as methanol because there is only one carbon. Now, another example could be CH, as I gave you here, the two are the H groups and one is R group. So the H, now this is the functional group OH, and now CH3. Now, this is actually CH3, CH2, and OH. So I can write it CH3, CH2, OH. And what would be the name of it, Zena?
Would it be, oh, ethanol?
Ethanol, yes. So this is also an example of primary alcohol. I hope it's clear.
Yeah.
All right, now secondary alcohol. But as far as secondary alcohol is concerned, so what you need to do is you need to put two carbon atoms or two R groups, sorry. So it would be like COH, H, and now this could be CH3 and this could also be CH3. Now this becomes, as you know, that we need to take the longest chain, so this would be the longest chain, right? Now, let me number it. It would be one, one, two, and three. So as the main chain is made up of three carbon atoms and the OH group is on the second carbon atom, so three means pro, right? So it would be propan, two, ol. Why propan? Because there are three carbons. Why 2-ol? Because the OH group is on the second carbon atom. So that means second carbon atom. So propan 2-ol is an example of secondary alcohol. Is it clear, Beta?
Yeah.
All right. Now the last one, tertiary alcohol. So as I have already told you that all the three groups or the OH is linked to the carbon atom, which in turn is linked to three R groups, is called as tertiary alcohol. So I'm going to take the simplest R group, that is CH3. So C, again CH3, this one is an R group, this one is an R group, and the third R group CH3, and then it is linked to OH. So now again I am going to take the longest carbon chain, that would be this. So or yeah, you can take this or you can take this, whatever is easier for you, right? So I'm going to stick to this one. So this is the main chain. Again, it's of three carbon atoms, one, two, three. So this is now, if you check on the second carbon atom, you have on the second carbon atom, you have a methyl group and you have OH group on the second carbon atom. The second carbon atom is linked to methyl group and OH group. So it becomes 2-methyl propan, 2-methyl small dash propan 2-ol. So this is the name of this compound and this is the tertiary alcohol. So 2-methyl propan 2-ol is an example of tertiary alcohol. Now, all the three are in front of you on the screen. If you have any problem, you can discuss it. If it's clear, then we can go further along.
It's clear.
It's clear? So these are the examples of primary, secondary, and tertiary alcohol. I hope it's all clear. Now we will, Alhamdulillah. Now we will shift to, Alhamdulillah. Now we will shift to the other one, that is a halogenoalkane, but I think there is no need to talk about the halogenoalkane in terms of primary, secondary, and tertiary halogenoalkane. But still, that's better. Anyway, I'll do it. Halogenoalkane. Now, you know, halogenoalkane means that a halogen atom is linked to the alkane. Now, Betty, this is, this is, let's suppose Cl. This is the easiest halogenoalkane or the simplest halogenoalkane, which is called as primary halogenoalkane. Why? Primary halogenoalkane. Why? Why? Because Cl is linked to the carbon, which in turn is linked to three hydrogen atoms. Now, this is the simplest one. So, what do you call it?
Chloromethane.
Well done, chloromethane. Now, if you again, and this is primary halogenoalkane, the other one could be you can change this H with CH3, right? So it would become ClCH, and CH3. Now, as there are two carbon atoms, so it could be written as CH3, CH2, Cl. And what will be the name of it, bitter?
Um, Chloroethane.
Yes, chloroethane. Well done. So it would be chloroethane. Again, it is an example of primary halogenoalkane. The reason being that the chlorine is linked to the carbon, which in turn is linked to two hydrogen atoms. That is why it is called as primary halogenoalkane. Now comes the secondary halogenoalkane. Now I am changing it with Br, then C, now CH3, and H. Now this is an example of secondary halogenoalkane. Why? Because the bromine is linked to the carbon, which in turn is linked to two CH3 groups. So this is called as a secondary halogenoalkane. As far as the naming is concerned, again you need to take the longest chain beta. This is the longest chain comprising of maximum carbon atoms. So there, these are the three carbon atoms. So that means propane. And this is bromine. On the second carbon atom, you will start the numbering from here, from either side, right? So you are going to get bromine on the second carbon atom. So this would be 2 bromo propane. So this is the secondary halogenoalkane. I hope it's clear.
Yeah.
And the last one is tertiary halogenoalkane. So if I have this iodine and then all the carbon valencies of carbon is satisfied. So let me write the abbreviated form of secondary halogenoalkane. Now the tertiary halogenoalkane would be like this. I can replace it with X. I can replace it with X. You know, X is a halogen atom. It could be fluorine, chlorine, bromine, and iodine. So I am putting three CH3 groups here. This is the tertiary halogenoalkane. Now, again, Betty, you will pick the longest chain. So, whatever the case may be, this would be the longest chain. Again, you will start numbering. So, 1, 2, and 3. Now, on the second carbon atom, you have methyl group and you have iodo group. So, what could be the name of this compound, Zena?
Would it be 2
Mm.
methyl bromopropane?
Uh, iodo. This
Oh,
is
2
iodine.
methyl iodopropane?
2 methyl, 2 iodo, right? 2 methyl, 2 iodopropane. You need to tell about the position of the iodine group, yeah? So it's on the second carbon atom. So 2 methyl, 2 iodopropane. Does it make sense, Peter?
Yeah.
2 bromo. Uh, all right, one thing, one change you can make. Uh, I comes before M, so it's better to write like 2 iodo, 2 methyl propane, 2 iodo, 2-methyl propane. Why? Because why I'm changing this? Because I comes before M. Does it make sense?
Yeah.
So now the name would be 2-iodo-2-methylpropane. The first name was also correct, but alphabetically, it should have been written 2-iodo-2-methylpropane. So that's why I wrote it like this. So this is beta tertiary halogenoalkane, secondary halogenoalkane, and primary halogenoalkane. Now, beta, we have done for alcohol as well as for halogenoalkane. I hope that both of these classification or the nomenclature is clear to you. Yeah?
Okay. It is clear.
Yeah. Any question, beta?
No.
All right. One thing, keep this thing in mind, beta, that you have to write it in this way. If in the exam, if it comes, you need to write it in this way. It will be easier for you to explain it in these ways instead of writing in this form, in this form. All right. Okay. Now, this was the something about the um, primary and secondary thing. Now we will start chapter number 12. Oh, I forgot to put the date. By the way, Zena, if I'll give you the homework from your book, would you be able to do it better?
Yeah.
All right, fine. So I'm going to give you a homework today related to the previous topics. So, Peter, you will have a whole week to do those homeworks. And after that, we will. You can post it on the WhatsApp group. After doing the homework, you can post them on the WhatsApp group, right? So, would it be fine if I'll give you 2, 3 types of homeworks related to the
Yeah.
classes of the organic compound?
Yeah,
All right.
that's fine.
Oh, that's wonderful. All right. Now we are going to study alkanes today, right? So this is 12.1. 12.1. As far as alkane is concerned, beta, we have done a lot about it. So if I will ask you to tell me the general formula of alkane and some nomenclature, that means some naming, and then branched chain alkane. Nomenclature or branch chain could come in the same thing. Alkane. All right. And then after that, we you can tell me about the isomerism. We have done this. We have done this. Although I am going to I'm going to tell you in the form of skeletal formula today. And then we are going to discuss the physical properties. By the way, now can you tell me a few points related to these captions, general formula?
Would it be CnH2n plus 2?
Yes, well done. Now, nomenclature, for example, if I'll ask you to name any alkane, then what name can you tell me?
Propane.
Propane. So, can you tell me the formula of propane?
Propane C3 H8.
All right, yeah. So N is equal to 3. So C3H2 times 3 plus 2. So 3 C3 3 times 2 6 6 plus 2 8. But this is the molecular formula. This is the remember we did about different types of formula, yeah? So this is
Yeah.
a molecular formula. Can you change it into structural formula?
Would it be three carbon atoms bonded to one hydrogen?
Yeah, well done. This one, right?
Yeah.
Now, but if I ask you to change it into skeletal formula, what it would be?
Um, three diagonal, like zigzag points.
V,
Yeah.
inverted V or proper V. All right. So this is, look, this is 1, 2, 3, or 1, 2, 3. So this is the skeletal formula representation of propane. Is it clear?
Yeah.
Good. And can you name any branch alkane?
Um, 2-methylpropane.
Well done, well done. So two, I'm going to write two, two methyl propane. So let's one. Yeah, can you help me drawing the formula?
3 carbon atoms.
Yeah.
And the middle one branches into methyl group,
Two
and
methyl
the
group.
rest 1 methyl group.
Yeah, one methyl group, right. So this is called, oh, sorry. This is called as 2-methyl propane. All right. And this is called as branched chain alkane. I hope it's clear. Now,
Mm,
at the last point, isomerism, we have already done that, right? Do you remember what type of isomerism was there?
Isn't it like it has the same
For,
formula but different
yeah,
structure?
yeah, for pentane. If I'll ask you to do it for pentane, so what would be what type of isomerism would be there for pentane?
Um,
Isomerism in pentane. The very first thing, you know what type of isomerism is there? It's like chain isomerism. Chain isomerism. If you remember, I'm going to quickly scroll up. I'm sorry for the here it is. Isomerism. So if you check, isomerism is of two types, structural isomerism and stereoisomerism. And the first type of structural isomerism is the chain isomerism. Yeah. So I'm going to stick to this one, that because in case of alkane, there is no positional isomerism. And functional group isomerism would not be there for alkane, because if I'm going to show you this functional group isomerism, that means I need to change the functional group. I don't want to do that. As far as position isomerism is concerned, so it can't be done in case of alkane, because the position functional group is simply the single bond. So you can't change the position of the single bonds. Had it been double bond or triple bond, you can change the position of a double or a triple bond, but you can't do it in a single bond. However, the only type of isomerism which would be there in alkane is chain isomerism. So we'll discuss that. Is it clear?
yeah.
So here it is. Isomerism in pentane, chain isomerism. So can you help me in drawing? As far as pentane is concerned, it's C5H12, which is the molecular formula for pentane. Now, chain means you need to differ differ the chain. So which chain? Carbon chain. So Betty, can you start off with the simplest one for pentane?
Like an example of chain isomerism.
Yeah, for pentane.
Will mm, 2-methylbutane work?
Yeah. So first of well done. First of all, you will start with the longest chain, Betty. Longest chain. The longest chain would be of 5 carbon atoms. So one, two, three, four, five. So this is the normal pentane. Let me write this. So you need to add N-pentane. Yeah. So I have written it quickly, so that's why it looks like that I have written small h, but it's not a small h, it's capital H. Always keep this thing in your mind. Right. So this is N-pentane. What is the meaning of N-pentane? Normal pentane. So this is the first isomer being formed. Now you are absolutely right. For the longest chain is of 5 carbon atom. Now you need to uh, decrease the length of the chain, so that would be a 4 carbon atom. So that means that this methyl group would go as a branch, not on the last or terminal carbon atom, because if I'm going to put it here, then I have to take the longest chain. So you need to put it on the middle carbon atom, right? So absolutely correct. So the second one would be, as you said, 2-methylbutane, right? So I'll start from here. So this is 2-methylbutane, because the main chain is of 4 carbon atoms now. Four carbon atoms. Now, what is the third one, Betty?
Um, uh, 1,2-methyl propane.
1,2 methyl propane. All right. Uh, uh, Betty, if I will put here and here, so what do you think, Betty? Uh, you are going to take the longest carbon chain, Zena. So, don't you think this would be the longest carbon chain? Yes?
Yeah.
And you know what? So, this is the longest carbon chain, so it is of four carbon atoms. But as I told you that you need to decrease the number of carbon atoms in the chain. So if it's five for the first one, four for the second one, then you need to have three for the third one, three carbon chain. So this is not going to serve the purpose because this would be between one, two, three, four, and because you need to start the numbering from the side from where the branch would be closest, so that would be one, two, three, four, and this would be 2 methyl butane. So it would be the same as this one. Are you getting my point?
Yeah.
So what would be the third one? You need to keep the chain now of three carbon atom. First four, now minus one, three. So one, two, three. Now, as I told you earlier, you can't put the fourth carbon atom on the terminal carbon atom. As soon as you are going to do it, let's suppose if you are going to put it here, then this would be the longest chain, right? If you are going to put it on this side, I'm talking about one carbon, then I'll put the other one like this, right? So now again, this is the longest chain and it would become branch. If I will put a carbon atom here and the second carbon atom here, this would be the longest chain and this would be a branch. So the longest chain would be of four carbon atom. I want to keep the longest chain of three carbon atoms. So what should I do, Zena?
A 2,2-methyl propane.
Well done. Shabash, beta. So I am going to put one methyl group here and the second methyl group here. All right, beta. So this would be the um this would be the um third isomer, and this would be the main chain. That's the most important thing of three carbon atoms. So now you will start the numbering from any side because from wherever you number the carbon atom, two methyls group would be on the second carbon atom. So the name would be 2, comma 2 dash dimethyl, and the main chain is of three carbon atoms. So I will write what?
Uh, propane.
Propane. Well done. So this is the third isomer. That means pentane can make three isomers, three isomers, and all of them are of chain isomerism. I hope it's clear. And its chain isomerism beta is a type of a structural isomerism. Hmm? All right.
Yeah.
All right, good. So this is about the isomerism in alkane. Now comes the next point, that is physical properties. Physical properties of alkane. Now, when I talk about the physical property, always keep this thing in your mind. I need to talk about the state. I need to talk about the color. I need to talk about the density or boiling point or melting point or type of bonding. These are the physical properties. All right. So if we talk about the properties of alkane, the very first properties is number one. Let me write it. This is a simple example of alkane, that is propane. So only two type. It's a type of a hydrocarbon. You know that hydrocarbon means containing carbon and hydrogen only. So this is propane. Only two atoms could be seen, carbon and hydrogen. There is a very slight difference of electronegativity between carbon and hydrogen. So I can say that they are alkanes are almost non-polar. What is the meaning of non-polar? You know that if carbon atom is linked to an electronegative atom, like chlorine, which is electronegative in nature, which is going to attract the shared pair of electron towards itself, getting a partial negative charge, giving a partial positive charge to the carbon atom. Now, when these poles come, this is called as polarity. So halogenoalkanes, they are polar in nature. But when we discuss the alkanes, as I told you earlier, there is a very little difference in the electronegativities of carbon and hydrogen. So we say that alkanes are non-polar. So there would be no uh, production of charges, partial negative and partial positive. Is it clear?
Yeah.
So alkanes are almost non-polar. Why? Because carbon is having the electronegativity 2.5 and hydrogen is having the electronegativity 2.51. So if you subtract the values, you are going to get zero point 0.4. That's the difference between the electronegativity, and this doesn't count at all. All right. So this would be non-polar. So the only if it is non-polar, when there is a polarity, which types of forces could be there, Zena? When there is a polarity, so which types of forces could be there?
Oh, like Van der Waals forces?
Yeah, and what type of van der Waals forces? Well done, very well done. If
Um,
polarity could be there, then
it's a hydrogen bonding.
no, not a hydrogen bonding, because for hydrogen bonding you need to have FON or NOF, right? There is no FON or NOF, so you can't say that it has hydrogen bonding. Yeah, so the only type of van der Waals force which could be there in alkane, that would be temporary dipole induced dipole. In this we will have permanent. In halogenoalkane we have permanent dipole, but not in this chloromethane we would not have hydrogen bonding, because hydrogen bonding needs NOF, and we have chlorine, so there would be no hydrogen bonding. But we would have permanent dipole interaction. You know that permanent dipole interaction is a type of van der Waals forces. If you remember, van der Waals force is of two types. Can you name it?
Um, oh, London forces.
Yeah. So the first one is permanent dipole interaction. The second one is called as London dispersion forces, which is present in all the molecules in the world, right? Or it can also be called as temporary dipole induced dipole. Yeah. So these are the forces which are present. Now, permanent dipole, which is termed as P dot D dash P dot D. This is in one molecule. This is in one molecule, and this is in another molecule. You know that van der Waals force is a type of intermolecular force. So when I say intermolecular force, inter means between. So intermolecular force means a force between the two molecules. Yes, Beta?
Yeah.
All right. So, as I told you, that if there would be a difference of electronegativity, then we are going to have permanent dipole interaction. And if there is no difference of electronegativity, like in alkane, then we would have London dispersion forces, which can also be called as temporary dipole induced dipole or London dispersion forces. So, alkanes are almost non-polar in nature. The only type of intermolecular, I'm sorry, the only type of intermolecular forces between the molecules are the weak van der Waal forces. And which type of weak van der Waal forces? London dispersion forces. London Persian forces. All right. And actually, although it's weak, but if the molecule is large, then the London dispersion forces would be also greater. And I'm telling you a very important thing, that London dispersion forces, they can change the state of the compound or the element, right? So that means, in case of, is it clear? This is a very important sentence I have written, that London dispersion forces can change the state of the compound. Yeah. So if, I'm sorry. So if we will start with with the simplest alkane, methane, then comes ethane, then propane, then butane, and then pentane. All right, till butane or somewhat pentane, these are the gases. All right, and then from hexane onwards, hexane we onwards till C10, we have all those, not C10, it should be C12. So we have liquids. From C13, semi-solid would start, and from C16 or 15, we have proper solids. All right. So what does it mean? It means the larger the molecule. Now the important point, the larger. Now look, what do I mean by larger? This is C1, C2, C3, C4, C5, C6, then C12, then C13, then C15. So the larger the molecule, comma, the stronger the van der Waal forces, comma, the and the state would change from gas to liquid and eventually solid. So you know that methane gas is used in cooking, or it is used in stoves for multiple purposes, right? So alkanes, they start off with gas, then they turn to liquid, and finally they change to solid. This is only because of the van der Waal force, is weak van der Waal force, which is actually London dispersion force. And after that, if the state changes, what else would change, Zaina?
But the bonds break.
No, any other property. If the state would change from gas to solid, what would also change, or what would be higher? Boiling point. Yeah. You know that
Mm,
gas, they have very low boiling point. Then liquid, they would have the boiling point in positive, but very low positive. And solid would have high positive. Are you getting my point?
yeah.
So boiling point, the second, the which property is this? Two, one, two, third property. All right. So the third property would be the increasing molecular intermolecular forces would result in the higher boiling point. So greater the length of the carbon chain, greater the length of the carbon chain in alkane, comma, greater would be the boiling point. I hope it's clear, right? The
Yeah.
shorter the chain, as I told you, that if the chain would be shorter, if the chain would be shorter, like butane, till butane, if the chain would be shorter, these are the gases. All right. And pentane is somewhat liquid. So, pentane having the five carbon atoms is liquid. But as I told you earlier, although the boiling point would be positive, but very low positive. So, it would be around positive 36 degrees centigrade, which is although positive, but very low positive. Are you getting my point?
Yeah.
And as we go along from carbon number 16, the alkanes would start becoming solid. And when they would get solid, definitely their boiling points would increase. Now, I'm going to tell you a very important point related to the boiling point, that alkanes, branching, effect of branching. Effect of branching. Like, what do I mean by branching? This one. This is a branching. For example, this is unbranched pentane. Now, I'm not putting hydrogens to save the time. You know that it is surrounded by hydrogen atoms. Now, this is unbranched bitter. This is unbranched. This is branched. Branched. And this is even more branched. You know, I'm writing the isomers. Yes, Zena, you know that I am writing the isomers, yeah?
Yeah.
So, Betty, this is somewhat spherical, all right? This is more branched. This is more branched. This is not branched. This is straight chain compound. Sorry. This is straight chain compound, right? And this is branch somewhat, but still it is not spherical. Look, this is not spherical. This is spherical, yeah. And this is one and the same thing. These are the isomers, right? So what I'm trying to tell you is that alkanes with branch chains, and now which would have the lowest boiling point? This is going to have the lowest boiling point. And why? Because it is extremely branched. So that means that alkanes with branch chains have lower melting point than the straight chain. This is straight chain. So alkanes with branch chains have the lower boiling point than straight chain alkanes with the same number of carbon atom. You know very well. One, two, three, four, five, same carbon. One, two, five carbons. One, two, three, four, five, five carbons. One, two, three, four, five, five carbons. So the number of carbon atoms remain the same. So I'm repeating, alkanes with branch chains have lower melting point than strict chain alkanes with the same number of carbon atom. This is because that they cannot pack together as closely as unbranched, and so the van der Waals forces are not very effective. Now this is properly packed. Now, when this is properly packed, then what is going to happen? That it would take a shape of sphere, and this would have the highest volume. Okay, I'm not going to relate it to the volume. It would make the things complex. I'll keep it simple. That when when the alkanes have branch, then what happens? They have the lower boiling point because they cannot pack together as closely as unbranched chains, and so the van der Waals forces are not so effective. So in this beta, van der forces forces are not very effective. So if the van der Waals forces would be less in number, then their boiling point, or their boiling point would decrease. So repeating again, that alkanes with branch chains, they have lower boiling point. This is because they cannot pack together as closely as unbranched chain. All right. So these are the points of contact. Have a look, beta. Let me explain in another way. Although it's not written in your book, but it will make the things very clear. you have to break all these points of contact, um, these points of contact, these points of contact. All right. So that is why the melting point is higher. Now, in this case, these are shielded. So you simply need to break these points of contact. That's it. So these are shielded. So if you cannot, no energy is required to break these points of contact. That is why less energy is required. So the melting point, oh, sorry, the boiling point would decrease. Does it make sense?
Yeah,
Any confusion, beta? If you have any confusion, Zena, feel free to ask, bache.
it makes sense.
All right, good. So, third, boiling point effect of branching is very important. Now, the fourth point, solubility. Solubility. Always, again, it depends on the carbon chain. It depends on the carbon chain. Greater the carbon chain, greater the carbon chain, lesser would be the solubility. Lesser would be the solubility. Let me tell you this thing, that if the carbon chain is greater, that means that hydrophobic character would be greater. So the greater the length of the carbon chain, hydrophobic character would be more. Phobic character. What is character? What is hydrophobic character? Water heating. So what does it mean? That means I have made how many carbon? One, two, three, four, five. So that means five carbon atoms. And if I am going to compare it with something having 16 carbon atoms, so that means that this is less soluble as compared to pentane, which is more soluble. So the greater the number of carbon atom, greater would be the insolubility. However, alkanes are insoluble in water, are insoluble in water. Why is this so? Because there is no charge. There is no charge separation, no charge separation in alkane. Why? Because as I told you, there is no difference of electronegativity. So you know that water is charged. HOH, water, H2O. It's better to write water like this. So as you know that oxygen is very electronegative in nature. So it is going to get a partial negative charge, giving a partial positive charge to the hydrogen atoms. So that means water is polar. So you know that like things dissolve in like things. So if water is polar, so if something is polar, it would be dissolved in water. If something is not polar, then it will not dissolve in water. Same goes here. In case of alkane, there is no charge separation, and rather there is no charge on in alkane. So that means that it is they are not going to be soluble in water. Secondly, greater the carbon chain, greater would be the hydrophobic character. That is another reason for the insolubility of alkane in water. Is it clear?
Yeah,
Any confusion, Bitte?
no.
All right, fine. Now, the last point, that is reactivity. All right. Alkanes are highly unreactive. Why they are highly unreactive? Because of the strong, let me write this. Now, sigma and pi bonds are not in your syllabus. Otherwise, I would have told you that why they are highly unreactive. Anyway, still, I'll tell you that alkanes are highly unreactive because of the strong, this is a very strong bond between carbon and carbon. And there is another strong bond between carbon and hydrogen. So carbon and hydrogen strong bond and carbon strong bond make the alkanes highly unreactive. Why is this so, bitter? Because you know what? If the bonds would be strong, then what is going to happen? A lot of energy is required. A lot of energy is required to break this bond, required to break a strong bond, strong bond. And because there would be a lot of energy which is needed to break the bond, and it cannot be attained easily. So that is why they will be no, they will be unreactive, because if the bond will not be broken, it is not going to react with something. So that is why they are called as they are highly unreactive. All right. And that is why, although it's not written like this in your book, that they have strong, as I told you, that I would have used the word sigma bond. This carbon hydrogen bond is a sigma bond. This carbon carbon bond is a sigma bond. But there is no discussion on the sigma and pi bonds in your book, so I'm not going to discuss it. However, I'll tell you this, that these bonds are strong bond. A lot of energy is required to break these bonds. So that's why they are highly unreactive. When I say that they are unreactive, it means that they are not going to react. They will not react, number one, with acids. They will not react with acids. They will not react with bases. They will not react with oxidizing agent. They will not react with any reducing agent. However, if you are going to provide heat to them, a very strong heat, then they will break down. These bonds would break down. If you are going to provide very, very strong heat in the form of temperature, then these bonds would get broken. And what is going to happen? Let's suppose if I have ethane, so these are the bonds. I'll show them with these two colors, and the other bond between carbon and carbon. So these bonds would be broken in the presence of a heat, or at a very high temperature. And when they would break in the presence of oxygen, what is going to happen? All these bonds would get broken, and these hydrogens will combine with oxygen to make water. And these two, just a minute. Mm. These two carbon will combine with oxygen to make carbon dioxide. So a high temperature treatment is required to break these bonds. And when these bonds are broken and carbon dioxide and water will be formed, so much energy is evolved that you can cook food on it. Is it clear? But it requires this reaction requires, which is combustion. This reaction requires a lot of oxygen, or in other words, you can say ample supply of oxygen. Then you are going to get so C2H6 plus O2. So you are going to get carbon dioxide and water. So can you balance it, Zena?
Will it be two, two in front of the carbon dioxide,
Well done. Two, yes.
and then three in front of the H2O,
Well done, well done. So here it is. Uh,
and
yes.
will it be 7/2 on oxygen?
Why 7/2? Why not 3 by 2? Or just a
Because
minute.
seven.
Okay, fine, 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 fine. You are right. 3, 7. Yes, 7/2. Well done. So that means that, so this would be the carbon dioxide moles and water moles, right? So if you are going to supply ample oxygen, then carbon dioxide and water will be formed. However, if the supply of oxygen would be less, then you are going to get carbon monoxide or carbon as well. And you know that carbon monoxide is a very fatal gas. All right. So is it clear?
Yeah.
So this whole chapter is clear. Any question, Bitte?
No.
All right. So Bitte, do make a concept map that keep alkane in the center, and then write the homologous series. Number two, they end in ane, CnH2n plus 2. Then you can write about these points. Number one, for example, um, they are non-polar, everything like this, non-polar, then highly unreactive. Now, you know what? Make an arrow down to write down the reasoning. For example, if I say that alkanes are non-polar, then that means this arrow down means question mark. Then why they are non-polar? Then you will write very small difference in the electronegativity of carbon and hydrogen. I told you carbon is 2.5 and hydrogen is 2.1. So the difference would be zero point 0.4, which is very, very less, right? And they are highly unreactive. I have again arrow down. That means you need to reason it out. So why they are highly unreactive? Because they have a very strong carbon-carbon and carbon-hydrogen bond. And you have to supply a lot of energy to break these bonds, and that energy can be given only in the form of temperature. So that is why when you turn on the stove and you light the gas with the matchstick, then or with a spark, then what happens actually that so much energy is evolved, and the methane which is in the stove, it changes to carbon dioxide and water, and so much energy is evolved that you can cook food on it easily, right? So in this way, Bete, then you will write show isomerism, then you will give different examples, and then you can talk about solubility and so on, right? I'm not writing everything down, Zena, because I want you to do the concept mapping yourself, right? For example, I have left the solubility, yeah, no, effect of branching. So a boiling point, I haven't discussed boiling point, so you can add boiling point as well. Then you can also discuss about that they are highly unreactive. After giving the reason that why they are unreactive, you can also write said that they will not react with acid or base or oxidizing or reducing agent. They will simply combust to give carbon dioxide and water. So, Zena, may I expect a very detailed, because you know, but this organic chemistry is the most important part of chemistry, right? So I do want you to have a very clear idea about all the classes of compounds. So, Zena, may I expect a very detailed concept map like this from you as a homework?
Yeah, that's fine.
All right, very well done, Betty. So, inshallah, when we will be having our next class, I'm going to post some homework from your book. And what you can do is you can do each homework every day. And inshallah, when we will be having our next class, then you can show me the homeworks, or it's better to do it on daily basis. Let's suppose if I'll post 4 5 homeworks, you will when you are done with the first homework, you can post it on the WhatsApp group, and I'll check you and give you the remarks, right?
Yeah.
Is it fine, bache?
Yeah, that's fine.
All right. Any question from today's lecture, Bete? We, s-
No.
we started from here. Yeah, we started from here. So if you have any question, you may ask, Beta. This is also very good. This is also very good. So these are the different things we have discussed. All right. All right. So is it fine, Zena? If you have no question, then it's fine, right?
Yeah,
Okay. All right, Bete. Take care. Thank you. Allah Hafiz.
thank you. Allah Hafiz.
Yes.